Okay, today's lesson builds on what we talked about yesterday with Planck and Einstein. So now we're going to look at a topic called the photoelectric effect. So how it started was Heinrich Hertz did some experiments where he was trying to detect electromagnetic radiation on a coil of wire, and he would see it spark, right? So he'd see sparks coming off, which he knew that were electrons leaving the coil. And sort of by accident, he tried to see the spark better, so what he did was he put it inside of a dark box so that there was no outside influences and it was nice and dark, hopefully that he would see the spark better. And when he looked through the glass window, it seemed that the spark got worse instead of better. So you'd think that inside the dark box it would get better, but in fact it actually got worse. So then he thought maybe it had something to do with the glass window, so he changed the glass to a piece of quartz, and the spark got a lot bigger than what it was with the glass. So he figured there had to be something due to the glass, and he thought that because quartz doesn't block ultraviolet where regular glass did, then he thought maybe then the ultraviolet light shining on the metal had to do something with it. He never got any further proving it or trying to figure out why, but he just sort of left it at that. Einstein then came along and said that, well, what's happening is we have some sort of ultraviolet light coming in, it's hitting a metal surface, and because of that frequency, whatever the magic frequency is of that light source, that's going to cause the electrons to leave the surface. So Einstein sort of said, well, basically what we're dealing with is still Planck's formula, E equals hf, and the energy that UV light has, each photon has, that energy gets transferred to the electron. And if it's big enough, if it has enough energy, the electron then would leave. So he said basically the key to this thing is having the right frequency. So he said the threshold frequency, which we symbol as FO, is the key. So whatever that metal is, depending on whatever the metal is, it might have a different frequency than some other sort of metal. So basically the idea then is the energy that's going to release the electrons. We can't create energy, we can't just make it magically happen. So what happens is there's going to be some sort of work or energy that has to be used to get that electron off the surface. So what Einstein said is we could just modify Planck's formula again, E equals hf, and we say, well, some of that energy is going to be transferred to work to get the electron off, and that frequency it's going to be needed is that threshold frequency. So he called this the work function, so it's how much work the light gives up in order to get the electron off the metal. And so our threshold frequency, remember, is minimum frequency needed, or if we were given it to it in wavelength, we can convert it and use wavelength, and it would be maximum, because remember, our frequency and wavelength are vice versa. So in the formula it would be hc over lambda, so because the wavelength's on the bottom, it now would be a maximum. But it's the same logic no matter which one you use. So let's do a calculation. So it's asking what is the threshold frequency. So we just have to go work equals HFO. And because they're giving us it in electron volts, let's use our H as electron volts, so 4.14. And we just divide those, solve it for our threshold frequency, and that gives us the 2.4 to the negative 15. Next example, it's asking what's the work function if the maximum wavelength is 1.1. So we'd use hc over lambda instead of hf. So we do the same thing. This time it's in joules, so let's use our h as joules times the by speed of light and divide by the 1.1 times 10 to the negative 7, and that'll give us our answer that we have there, 1.81 to the negative 18. So pretty easy formulas in terms of dealing with work function, threshold frequency, threshold wavelength, whichever. So later on, Millikan set up a different experiment to kind of take this one step further. So he's saying, well, if we have an ultraviolet light hitting zinc like Hertz predicted, and we have electrons flying off, so what he said is, well, if we have electrons moving, we should be able to create electricity or create a current. So what he did was he set up a tube so we had no outside influence, shone the UV light on the zinc plate, he got electrons to go across to another plate, and kept it going, so the electrons kept going. So the idea is that we would get current going around the circuit. So the electrons would leave the metal plate, go around, build back up on the zinc plate, the UV light would shoot them off, and we just keep on repeating around and around. So he used an ammeter. So the ammeter, all that was for was to actually detect that there was a current. So if he has stronger UV or whatever, then maybe the current gets higher. If there's less, then it would show less current, or if it was the wrong light source, then nothing would happen. So that was just a way to detect how much current there was on there. So a couple of key things. So our electrons are leaving, so that would leave that plate positive. The electrons pile up on the other plates, that would make that one negative, and then our current flow, the electrons would go towards the positive plate. So what he also added to the experiment is trying to figure out how much energy those electrons actually had. So let me erase this. So we have our electrons going across, and we get our current flowing around the circuit like that. So the idea was then, well, how much energy do those electrons have? So we know they're moving, so it's going to have some sort of kinetic energy. So what he tried to figure out was, in order to calculate that kinetic energy, all we'd have to do is put a battery in there, and he reversed the battery. So you can see, in this case, the electrons inside the battery are going to go the other way. So our current is going to sort of battle each other out. So if our battery was weak, the electrons going around the wire are going to be stronger, so they just go through it, but they get slowed down a little bit. And if you made the battery really strong, then the battery would win the battle, and the current would go around that way. And so we wouldn't see anything on the ammeter. So basically what he did was he put a variable battery so he could slowly adjust it, and he basically turned it from 0, which was showing maximum current, and then he would increase that voltage, so the electrons are going to go opposite to the electrons coming around. And he basically would slowly increase that until those balanced out. So once the voltage increased and we got a 0 current, then at that point we know the two had to be equal. So he called it the stopping voltage, so the amount of voltage required to stop the electrons from flowing. And then he just modified an old formula again. We use voltage equals energy over Q. So energy equals QV, so we rearrange that and say, well, the EK max, the energy of those electrons, the maximum kinetic energy, is equal to the charge of the electron times whatever that stopping voltage is. So this formula says, determine the EK max. So it says electrons from a zinc surface if they give us electric field and a distance. So the only thing we have to do with this, remember, voltage equals electric field. It's electric field equals voltage over distance, so voltage will equal electric field times distance. So we just have to do that in our formula. So our EK max would be charge of an electron times electric field, which is 16, and times our distance, so 0.03 in meters, and that gives us the total energy that those electrons have. So what we're going to do is we're going to put all of these formulas together now into sort of a new formula that we use quite often. So we basically, in this situation, are really dealing with conservation of energy. We have energy coming in terms of the light, and then we have energy going out in terms of the electrons. So if we think of, let me kind of redraw this here, so we have some sort of light coming into a metal surface, so that energy will be HF, so E equals HF. Then we have the electron getting shot off, so that energy then would be 1/2 mv squared. But remember, there's also that work function that so much energy is going to be used to get that electron off the surface. So we can use any variety of this formula. So we can have HF for our light coming in. We'd have our work function of the metal plus our EK max. And sometimes we'll have to even go further. Our work function, remember, is HFO, and our EK max could be 1/2 mv squared. So we can do any of these, or you could even use for EK max, if it was a stopping voltage question, you could use Q times V stop as well. So either of those formulas would work. So all you have to do is plug in whatever situation they give you. So for this next example, it says threshold frequency And we have EMR coming in, it's asking for our speed of electrons going out. So we need to go HF coming in, HFO for the work function, and then 1/2 mv squared for the electrons going out. So we just need to plug all those in. So 6.63 for our H. Our frequency in this case is, they give us wavelengths, so we're actually going to have to use HC over lambda instead. Okay, so we'll have HC over lambda, so we have 6.63 times our 3 to the 8th, and we divide that by 2.5 to the -7. And then on the other side, we have H again, so our 6.63 to the -34 again, times it by our threshold frequency, which they give us as 1.14 to the -15, and then we'd have 1/2 times mass of electron times v squared, and then we just solve it for velocity. So I won't bother doing this calculation. You can see you just plug in all the numbers, solve it for v, make sure you square root it, and that's it. So quite simple. Like when you're dealing with these formulas, sometimes they might just say we have 6 electron volts of energy coming in. It requires 2 electron volts of work to get it off the metal, and then I might ask what's the K max. So we just go 6 minus 2 is 4. So that's as simple as it gets, or it might be complicated where we have to plug in all the numbers and solve it for velocity or whatever, like we just did in this example. One last thing to look at when we're dealing with photoelectric effect is quite often, just like any other thing, graphing will sometimes help us understand what's going on. So if we graph photoelectric effect and we think about, well, it's not going to have any energy, the electrons are going to do nothing till we hit a threshold frequency. So if we draw a graph, we just get a nice straight line. And what happens is we graph energy versus frequency. So we know the threshold frequency has to be the x-intercept. So anything beyond that frequency, then our electrons would leave. And anything less than that is just going to be used up by the work function. So we get a couple of key points. The first one is our x-intercept is the threshold frequency. And the y-intercept ends up being our work function. So those two values are pretty important. And then, because we're dealing with energy equals HFO, if we do rise over run, so the energy over frequency, that'll end up giving us Planck's constant. And it doesn't have to be FO, I just picked that formula, but it works whether any frequency. So you can see then rise over run, which is slope, which in this case is energy over frequency, ends up being Planck's constant. So the slope of the line will always be Planck's constant. And because it's constant, it's going to always be the same. So what that means is if we graph different metals, so this example here, it shows copper, selenium, and calcium, and it's showing 3 different lines. So what that means is each one has a different threshold frequency, so we have different values here. So that means each one's going to have a different y-intercept as well, so a different work function. But what you do notice is they're all the exact same slope. They're all parallel lines. So that means Planck's constant has to be the same for each, which it is. So you're always going to get parallel lines. So you can see in the formula we have HF equals EK max plus work. If we rearrange that for energy, so we'd have Y equals HF minus W, and you can see that we basically get a slope of the equation of a straight line. So our H is our slope, our X is our threshold frequency, our y-intercept is our energy, which in this case is our work function, and that's it. So to answer this question, now you can see it's asking which line is which. So if you look at the 3 numbers, selenium has the largest work function, so that means it's going to be the highest threshold frequency, so that means the green one has to be selenium. And you can see the next highest is copper, so that means that's the red one. And our last one with the least work function would have the least amount of threshold frequency, so that would be our calcium. And that's all for this topic.